third lecture I'm giving, and I title all three Attosecond Physics, Near Future Prospects, because in my group, the problems we're working on are sort of just beyond where experimentalists can do experiments nowadays. The first lecture, to remind you, had to do with the new physics that will become possible when intense attosecond pulses become available. The second lecture had to do with the kinds of physics in observing electron motion in targets that can be done using ultra-short electron pulses, attosecond electron pulses. In this third lecture, we'll focus on applications of circularly polarized attosecond pulses. Right now, almost all attosecond pulses are linearly polarized. Margaret Murdane's group has shown ways to produce circularly polarized pulses in the X-ray region, or the XUV region. And so I will just give two examples, and let me say that, as Lars indicated before, nowadays theory is complex, and it needs different kinds of expertise. And so this work I'll be presenting involves a number of collaborators. The lead and first author on all the work is my postdoc. He's now a research assistant professor at Nebraska, Marcel Ngoko Jokam. My former postdoc, Suchin Hu, who is now in Rochester, was involved in this work, as was Lars Madsen, and my longtime Russian collaborators, Nikolai Manikov and Alexei Neramian at Voronezh State University. What I'm going to talk about are first the numerical developments, although I would have to spend at least an hour going through in detail, and as you saw from Lars's talk was a good introduction. I'm going to be very brief on the numerical developments, but just point out the new aspects in this work. Basically, we have solved the two-electron time-dependent Schrödinger equation for one or two arbitrarily polarized XUV pulses, and this is the key aspect because we're looking at circularly polarized XUV pulses, and that fact increases the dimensions of a calculation. Most work that involves solving the two-electron TDSE simplifies by one dimension by only looking at linearly polarized pulses. I'm going to give two examples of new physics that can be done with circularly polarized attosecond pulses or elliptically polarized. One is nonlinear attosecond physics. This involves intense attosecond pulses, and this work was reference to this work is here. And each of these PRL papers has some supplementary material which gives more detail about the methods used in the numerical method. And then I will finish with a very recent result we obtained on linear attosecond physics, in which we showed that you can produce electron vortices when you photoionize helium by time-delayed few-cycle circularly polarized pulses. So, as I told you in my first lecture, our motivation began in 2006 with the achievement by the Milan group of single-cycle attosecond pulses of 130 attoseconds. The carrier frequency was about 36 eV. 2 years later, the Garkin group produced 80 attosecond single-cycle pulses of about a carrier frequency of 80. And 3 years ago, Zheng Cheng's group produced 67 nanosecond pulses with a range of energies in this region. As I emphasized in my first lecture, this is just a reminder, the physical interest is that when you have a few cycle attosecond pulse, it's the electric field that dominates the interaction with the target. And because it's a few cycle pulse, the carrier mode phase matters. The second key point for us is that in the XUV region, the large carrier frequencies, 36, 80, anything in that range, allows perturbation theory to work, which is extremely helpful for analyzing the numerical results. So, numerical methods. We solved the 2-electron time-dependent Schrödinger equation. This is it in its simplest form. For linear polarization, a large number of groups can solve that equation for 2 electrons. If it's a 5-dimensional problem, the m quantum number is conserved, and Su-Ching Hu has an optimized finite element discrete variable representation, time-dependent close coupling technique, which is a method we used, or we adopted it to the problems we are interested in. And elliptical polarization is a 6-dimensional problem because the laser polarization is not in 1 dimension, but it's rotating in a plane. The key idea for handling this numerically was by Harm Muller in this paper. And that idea is that the electric field seen by an observer in the rotating frame is always linearly polarized. So if you have a circularly polarized light, if you go to a rotating frame, it's linear polarization, and everything is more easy to treat for linear polarization than for circular polarization. Lars Madsen's group here in this paper, 2007, took that idea and made it a practical calculational scheme. And Marcel spent 2 weeks in Aarhus with Lars learning that material. So the key point of all of this calculation is that at each time step, the atomic interactions are treated in the lab frame, as usual. Then there's a rotation to the rotating frame in which the laser atom interactions are treated. And then you rotate back to the lab frame, and then take the next step. And so this is how this is done. And so I'm going to be very brief on this. If you want more details, look at the supplementary materials of our publications.
So for circular polarized light, in a rotating frame is just the DC field.
Excuse me?
So in a rotating frame,
yes,
the circular polarized light is just DC field.
Yes. 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 Oh. We wrote the code for elliptically polarized light, and there the magnitude is changing, so it's not a DC field for elliptical polarization.
It doesn't go to 0.
What?
It doesn't go to 0, right? Just it's theory in one direction. Just go
Yes,
up, down.
it's right.
Okay.
Okay, so the first application is circular polarized attosecond. Circular polarized is to nonlinear attosecond physics. We're assuming intense fields, and we've identified a new, what we call a nonlinear dichroic effect in double ionization of helium by an intense elliptically polarized few cycle pulse. And the lead author is Marcel here. This picture appeared in photonic spectra. And the key idea here is this. We're looking at double ionization of helium by an elliptically polarized attosecond pulse. As I mentioned before, we can treat the differential probability for ionization of 2 electrons with light having polarization E and the final electrons having momenta P1 and P2, we can treat it as a first order amplitude, that is 1 photon interacts with the target, and a second order amplitude in which there are 2 interactions of the XUV pulse with the target. And then the differential probability is the square of this, and of course the key approximation is to ignore the square of A2 and just take the interference term into account. How did we choose? The total dichroism is the difference in this differential ionization, 2-electron ionization probability between right elliptically polarized light and left elliptically polarized light. And for simplicity, I will only show you results for circular polarization. So the dichroism is the difference between the results for 2 different handedness of the polarization. How we chose our parameters is shown here. If you have long pulses, 10 cycles, our carrier frequency is 65 dB, which is below the threshold for double ionization. So a 1 photon absorption for a long pulse does not doubly ionize helium. The only way you get double ionization is if the system absorbs 2 photons. However, we use 3-cycle pulses with 65 dB carrier frequency. These have a broad bandwidth, as you can see here, of 31 eV. So this extends above the threshold for double ionization, but at the same time cuts down the amplitude here so that it's comparable to the second order amplitude for absorbing 2 photons. And so we are looking in this region here where you cannot tell if the electrons, the 2 electrons that are doubly ionized, absorb 1 photon or 2, because it's in this overlap of the 2 amplitudes. I should also say that we have a whole paper looking at the perturbation theory analysis of double ionization. There's one more. I explained our perturbation theory analysis for single ionization in my first lecture. Here we have another vector because 2 electrons go off in the continuum. So now there are more vectors. The whole point of a perturbation analysis is to take all the vectors and extract them analytically so that the coefficients of the different vector terms are only energy-dependent dynamical parameters that can be fit to an experimental result. But I refer you to this paper for the theory of how that's done when 2 electrons are in the continuum. I'll just show you the results of our perturbation theory analysis. Here, we define the absolute dichroism as I said, the difference between the double ionization for right and left circularly polarized light, but perturbation theory shows that there are 2 terms. There's a term called D1 that involves only the first order amplitude, and it is proportional to the intensity of the light. The interesting term, the new nonlinear dichroic term, is the one coming from interference of the first order amplitude and the second order amplitude. And this is the one we're interested in demonstrating results for. So we want to get rid of this. Doing the perturbation theory analysis allows us to eliminate this from consideration so that our results only depend on the nonlinear dichroic term. And the way that's done is we find from our perturbation theory analysis that the dichroism here, the difference between the first order term for right circularly polarized light and left circularly polarized light, can be parameterized in this way, where theta in the polarization plane, theta is the angle with respect to the propagation direction of the light. So that's pi over 2. So that's 1. Xi is the degree of circular polarization. I went through this in my first lecture. And you have the imaginary part of two scalar dynamical amplitudes. We call them Ungerada. The Ungerada term is 0 for equal energy. And so we have, for our results, we want unequal energy. But we want to get rid of this term. And so we see, oh, sorry, sine theta is not the angle with the k-axis. It's the angle between the two electrons. And if we choose theta equals pi, then according to perturbation theory, this first order term vanishes. And we are studying directly this new nonlinear dichroic term. The parameterization for the nonlinear dichroic term is this complicated two-line expression. Let me just indicate the features here. C is proportional to the probability that depends only on energy. We have the degree of circular polarization here, the degree of linear polarization here. We have the carrier envelope phase here, and everything depends on this FU, which is 0 for equal energy sharing, so we specify we want unequal energy sharing. And because we've chosen theta equals pi, we have to measure the electrons coming out back to back. This is helpful because if you're solving the two-electron time-dependent Schrödinger equation, as Lars mentioned, there is no exact solution for two electrons in the continuum in a Coulomb field. And so if they're going in opposite directions, you minimize their interaction. And so after the pulse is done, we wait about half a femtosecond before we project onto free electron states. One going this way, one going this way. By that time, our results are converged when we do that, which means that they're far enough away that the results don't change if you wait longer. And these H's, H primes, these are all dynamical parameters. You can look in our papers for expressions of what those are, but they can also be fit. All of these other parameters, the L's and the phi is the angle with respect to the major axis of the polarization ellipse. They are analytically extracted here. So these are the results, and I'll go through them rather quickly. So this is unequal energy sharing case back to back. The electrons are going back to back. And these are for 4 different carrier envelope phases. This is 0, pi over 3, pi over 2, and 5 pi over 6. You can see how sensitive this nonlinear dichroic term is to the carrier envelope phase. Here, the blue dashed line and the solid line are, this is for the right circular polarization, and this is for the left. I'm sorry, it's not circular, it's elliptical, plus minus 0.8. And you can see that there's a difference. And this difference is the dichroic effect. Here, for a carrier envelope phase pi over 3, there's almost no difference. Here, it switches dramatically. And here, this is complicated, but we have extracted the L equals 1 term that comes only from absorbing 1 photon. And you can see that those are symmetric about this axis, as you would expect for when you absorb 1 photon. It's the interference term that causes this to be non-symmetric. So now the dichroism versus the carrier envelope phase, we subtract those 2 curves. And the solid curves are when we subtract everything, and the dashed curve here is when we keep only what in perturbation theory would be the nonlinear dichroic term, from the interference term. Since we're solving the two-electron time-dependent Schrödinger equation exactly, we include all perturbation orders. So there are some subtle contributions from third-order perturbation theory terms, which are reflected in this wavy line here of the blue dashed curve, which should in principle be 0 if we only had the first two orders of perturbation theory contributing. But you see, the approximation that they are the dominant ones is pretty good. This is the normalized dichroic effect, that is the difference here divided by the sum. You can see that it's very sensitive to the carrier-neutral phase. And perturbation theory predicts that the dichroic effect, this nonlinear, is proportional to the sine phi, which means it should be 0 at 0 and pi, and sure enough, it is in our numerical calculations. This is the dependence of the dichroic effect on ellipticity. It's 0 for 0 ellipticity, and it varies from circular polarization, gives you a result here. 0.8 that I showed you before is this curve, and then it gets smaller as the ellipticity goes down. This is the normalized ellipticity. And the dependence of this effect on intensity is rather stable. All curves, there are 3 different intensities here, 1, 1.5, and 2 petawatts, but normalized by the intensity to the 3/2 power. So the difference here is due to higher order terms coming in, but basically the dependence on the 3/2 power is pretty well confirmed by our numerical calculations. This is the dependence on the energy sharing. The 2 electrons can come out back to back, but they could have different amounts of energy. Total energy is 4 eV above threshold. But you could split the total 4 eV in various ways, and you can see how when they're unequal, you get the maximum dichroic effect. And so the conclusions for this first part are that a new type of dichroic effect, nonlinear dichroism, is predicted, and it is basically proportional to the 3/2 power of the intensity, indicating that it's the interference of a first order amplitude and second order. It's very sensitive to the CEP, ellipticity, intensity, and energy sharing. And the key point is it probes electron correlations on their natural time scale, since this vanishes for long pulses. For long pulses, this goes away. And let's look now at the second example. This is linear attosecond physics, so this would work even for weak attosecond pulses. We show that one can produce electron vortices in photoionization by circularly polarized attosecond pulses. This was on the cover of the September 11th, unfortunate date, but September 11th, 2015, cover of PRL, and highlighted in Nature Physics. And what's going on here? Here, we're ionizing helium by 2 pulses, 2 attosecond pulses that are time delayed in general. We've also looked at when they're not time delayed, but they're circularly polarized with either with the same circular polarization or opposite polarizations. And so this is a picture. The carrier frequency is 36 eV. These pulses are single cycle, full width, half maximum, and so they have a broad bandwidth. And so when it hits helium, ionizes electrons here and produces a wave packet, which then starts to move off. And then after some time delay, you hit helium again and create a wave packet that moves off. But the polarizations, you produce electrons in the helium ion with singlet P, m equals +1 or m equals -1 magnetic quantum number. Now, what I'm going to show you is that this is a highly unusual kind of Ramsey interference. The normal Ramsey interference in 1950 had to do with molecular states, but more recently, Ramsey interference has been observed in Rydberg states for linearly polarized light, for example, in Tom Gallagher's group, Gerber's group. In the continuum for linearly polarized light, Suching and I looked at that, but experimentally, Warnhaupt et al., this is 3 German groups collaborating. I think the lead group is Gerber's again. And this is from this paper. You can see what they're doing. They are ionizing some atom with a time delay, 2 linearly polarized pulses, and they look at what happens after 350 femtoseconds, I don't know. After 350 femtoseconds, the 2 wave packets are moving, but they spread. After 900 femtoseconds, they overlap. After 5,000 femtoseconds, you get this interference pattern in the continuum, and so they observed this. What we are doing is overlapping wave packets produced by 2 opposite circularly polarized pulses. Just to remind you of how we parameterize our field, it has some envelope function. The first pulse, it has a polarization E1, which is going to be right or left circularly polarized. You have a carrier frequency and a carrier envelope phase. The second pulse is time delayed with respect to this one, but the same envelope function. And it has a polarization E2, which will be opposite to this one. And time propagation is time delayed here, and it has a carrier envelope phase by 2. This is the definition of the polarization vectors. I've gone through this in my first lecture. The intensity we use in these calculations is 10 to the 14 watts per centimeter squared, but it could be lower. And now, let's just take 2 identical pulses. E1 equals E2, both right circularly polarized. Our perturbation theory says that the differential probability is proportional to some image-dependent cross-section here, sine squared theta, and cosine squared on this relative phase. The relative phase is here. It's the difference in the carrier envelope phases of the 2 pulses and the kinetic energy of the electron plus the binding energy times the time dependence. So this kinetic energy plus binding is the photon frequency. This is omega tau. But it's important to put the energy of the electrons here. And so you see that by varying the time delay, you can change cosine squared and change the magnitude of this. But there's no phi dependence. And so you get circularly symmetric results. If there's 0 time delay, then, if there's 0 time delay, then you just get a smooth distribution. These are the same pulses, and so if there is a time delay, here a delay of 500 attoseconds, then for that, as this is a plot in momentum space of the detected single